The final concepts we are going to talk about are spanning trees and minimum spanning trees. A spanning tree of a simple graph G, now we are going back to graphs, is a subgraph of G that is a tree containing every vertex. So it has to be connected and it has to be a tree structure, and every vertex should be connected to this structure. So this means you are going to select some of the edges, and you are going to leave some of them out so that you do not have any simple circuits. So you eliminate circuits. What you have is a tree, and we will call a spanning tree. Now, a spanning tree of a simple graph G may not be unique. And the way to obtain a spanning tree is, well, you can apply either depth first search or breadth first search here, and both of them will yield spanning trees. Take this one as an example and apply depth first search on this by selecting A as the root. Okay, so you visit A as the root, the first element, and then remember depth first search. You try to go as deep as possible. And then when you cannot, you backtrack towards the root where you can visit other vertices. So A has only a single neighbor, which is C, so you visit that one. Now C has two or rather three neighbors, A, B, and E. A is already visited, so you have to select between B and E. Again, this could be random, or it could be according to a certain rule. It could be lexicographical or some other rule. For instance, let's say we select B. And then since the only neighbor of B is C and C has been visited, you have to go back to C and then visit the other neighbor, E. Again, E has neighbors C, D, F, and C has been visited. So select one of D or F. Assume, again, lexicographical order, you select D. And then D has two neighbors, E and F. Well, you have just arrived from E, so you can't go back to E, so you have to visit F. Again, F has neighbors D, E, G, H, but D and E has been visited, so select one of H and G. If you select in a lexicographical way, it will be G. And G has two neighbors, F and H, so you need to select H. And from H, you can select I or K, because F and G has been already visited. If you select lexicographically, you select I. And then you will have to come back because I does not have any other neighbors. Come back to H and select the other neighbor, which is K. And then with J, you are finished. Now here you have 1, 2, 3, 6, 9, 11 vertices. So the spanning tree you find has to have 10 edges. Recall in trees, if you have n vertices, you will have n-1 edges. Therefore, this procedure will take as many as 10 iterations on this graph. Therefore, in this way, you can find a spanning tree. Let me repeat once again. Here we use the lexicographical order to select the next neighbor to visit, but that doesn't have to be like that. And a depth first search might produce different spanning trees if you select different vertices at each vertex. Also, the selection of root affects the structure of the resulting spanning tree. For instance, if you select F as your root, then you will have the selection of D, E, G, and H. Assume that you select H. Then you have the selection of I, K, and G. Let's say you select I. Then you'll have to come back and select one of G and K. Let's select G. Because I have come back from I, G will be connected to H. So I'm selecting this edge here. And then again, since F is already visited, I have to come back to H and I'll have to select K. But then from K, I can go down to J. Then this has been included. I have to come back to K and then to H and then to F because all of these are visited. And then from D and E, I need to select one. Let's say I select D. And then I have to select E. And then I have to select C because no other option. And then A and B, I can select either one. And this is the resulting spanning tree. As I said, depending on your rule for selecting among the multiple candidates, among the neighbors, and also depending on your selection of the route, the result will look different. And let's look at how you can find a spanning tree using breadth first search. On this example, on the right-hand side, let's assume you select E as your route. Again, let's assume I'm using lexicographical order for the selection of neighbors. So from E, I have B, D, F, and I, so I will have to select B. And then from B, I need to select, but recall a breadth first search, I need to also visit all the other neighbors, E to B, E to D also, E to R, E to F, E to I. So add D, add also F, add also I. Now, in this order, I visited B first, and then D, and then F, and then I. Therefore, I'm going to apply the same recursively to these in this order. First to B, E is already visited, so I need to add A and C. A and C. And then B is done, so come back. The next neighbor was D, so its neighbors are A, E, and H, but A and E are visited, so I need to add H. Okay, and then F. The neighbors of F are E, C, which are all visited, and then J, G, and L. So I'm going to visit them. J, G, sorry, L is not a neighbor of L, so I'm not going to visit just yet. And finally, I need to visit the neighbors of I in the second level. H is already visited, E is already visited, J is already visited. So the only one I can go to is K. Okay, so the level below the root is done. So E here, and then B, and then D, and then F, and then I. And from B, I visited A and C. And then from D, I visited H. And from F, I visited J and then G. And from I visited K. So I'm going to backtrack and look at the neighbors of A. Do I have any unvisited neighbors? No. Then I will have to look at C. B is visited, F is visited. So again, no other leaves here. So I look at H. D is visited, I is visited, K is visited. So again, no other vertices. So I look at J. I is visited, F is visited, G is visited. So I don't add them. And then I look at G. So I have L here. So I'll have to add L. L will be added. And then it will be added here. And finally, I will check K. H is visited, I is visited. The only one I need to add is M. And therefore, when I add M here, my spanning tree has been complete.